cosine of the quantity b plus a cosine of x over a plus b cosine of x. And they give us a little bit of extra information here. They tell us that x is strictly between 0 and pi, and that a is greater than b and b is greater than 0. Okay, now this extra information that we're given, the first thing that we're given is that x is between 0 and pi, and that makes sense because we want to make sure that in the end that our arc cosine function gives us the correct output. We have the correct domain values, and so that's what these extra rules are telling us at the end. Has to do with domain issues that are going on. The a and the b are constants, and that's all we know about it. All right, so Aaron, what are you thinking about when you wrote this down?
I did the chain rule first.
Okay. So this makes sense for the chain rule. We've got arc cosine of stuff, and so our outside function is arc cosine of x, and our inside function is b plus a cosine of x over a plus b cosine of x. All right, now a couple of things to notice here is a cosine, that's the a that's our constant, whereas arc cosine is the same as inverse cosine of x. Okay, so the derivative of our outside, keeping the inside the same, looks like y prime is equal to, okay, well our outside function is arc cosine of x, and so its derivative looks like negative 1 over the square root of 1 minus x squared. And that's a good one to memorize. I mean, we did come up with that formula, or at least for arc sine, and I asked you to go home and work on derivative for arc cosine, but it's a good one to memorize. So derivative of the outside, keeping the inside the same. So everywhere that I see an x here, I'm going to replace it with this entire inside function. So we've got y prime is equal to negative 1 over square root of 1 minus b plus a cosine x over a plus b cosine x. That whole fraction is squared. Okay, so far we have derivative of the outside, keeping the inside the same. Now our chain rule says then times the derivative of the inside. Now, to work with the inside, what rule do we have to use there?
Is that the quotient rule?
Yeah, we're going to have to use the quotient rule to take the derivative of the inside. So our derivative of the inside is going to look like low a plus b cosine x, low d high. So derivative of b is 0, and a is a constant, so we have minus a sine x, low d high, minus high, b plus a cosine x, d low, derivative of a is 0, and the derivative of b cosine x is negative b sine x, low d high minus high d low, draw the line, and square below, a plus b cosine x. Square that piece. All right. Derivative of the outside, keeping the inside the same, times the derivative of the inside. End of story. All right. Any questions about that one? Going once?
Yeah.
Twice? All right. Are there other questions about section 3.5? The practice problems out of there. Okay. So in that case, we also talked last time about 3.7. We skipped 3.6. 3.6 is derivatives of hyperbolic trig functions. And so we are skipping those. And moving on to L'Hopital's rule, which is section 3.7. L'Hopital's rule is a tool for calculating limits by using derivatives. Any questions out of the 3.7? Number 7. Number 7, we've got 3.7. Number 7, we're calculating the limit as x goes to 0 of tangent of p times x over tangent of q times x. Okay, so Andrew, what were your thoughts when you first looked at this?
I don't know.
Okay, so you wrote it down in your paper and you said, I'm not sure what to do with this.
I'm not sure what to do.
Okay, so the first thing that I would think of when I look at this is, I'd say, great, I have a ratio here, I have a division bar here, so I might want to think about how I can use L'Hopital. And so in order to use L'Hopital, I want to analyze what happens as x goes to 0. So in our numerator, we'd have tangent of p times 0. Now p and q are our numbers. We don't know what those numbers are, but they're constants. And in our denominator, we'd have tangent of q times 0. So what we're really asking is what happens to our numerator and denominator if we allow x to go all the way to 0. And what is the tangent of 0? Do you know? Yeah, it is 0. So the tangent of 0 is equal to 0. So we end up with 0 over 0, which is one of our indeterminate forms. And so this tells us that we can use L'Hospital's rule. Hardy har with no S, Mr. Hospital. Okay, so let's use L'Hopital. All right, so back over here, L'Hopital says that if we have a limit that's an indeterminate form, we can take the derivative on the top, derivative on the bottom, and our limit will still be the same. So we're going to have the limit as x goes to 0. Derivative on the top, well, derivative of tangent is secant squared, but it's not just an x inside the parentheses. So I need to use the chain rule when I take this derivative. So derivative of the outside, derivative of tangent, is secant squared, keeping the inside the same. So that's secant squared of px times the derivative of the inside. And the derivative of px is p. If you don't like the p, throw your favorite number in, maybe tangent of 3x. And then our derivative is derivative of the outside, keeping the inside the same, times derivative of the inside.
Just to make sure I have it right, say if it was just tangent x, then you wouldn't use the chain rule?
That's right.
Okay.
You could use the chain rule on that, and what would happen is this. You'd have y is equal to tangent of x, and your derivative would be derivative of the outside, keeping the inside the same, times the derivative of the inside, which is just a 1.
Okay.
And so technically, you're actually applying the chain rule every single time you take a derivative. You just don't worry about that 1. Okay, so that's our numerator. And our denominator is going to be really similar. We're going to have secant squared of q times x times the derivative of the qx, which is q. Okay, questions on those derivatives so far? All right, so I look at this and say, well, what the heck is this? Is this going to be useful at this point? And it actually is going to be useful because if I look at my denominator and my numerator now, in my denominator, if I allow x to go all the way to 0, what is the secant of 0? It's equal to 1. And if I wasn't sure about that, secant of 0 is the same as 1 over cosine of 0. And cosine of 0, well, that occurs on the unit circle over here on the right side, and so the x value is 1, the y value is 0, and we're looking at the x value. So this is 1 over 1, which is 1. So as x goes to 0, secant squared of qx goes to 1. This is in fact equal to 1. And secant squared of px also equal to 1. So we can let x go all the way to 0, and we end up with 1 times p over 1 times q, which is p over q. All right, any questions about this one? Going once? Twice? Andrew, does that work for you? Okay, cool. All right. The other way to think about this problem is to use Ben's theorem from earlier on in the semester and rethink this guy in terms of, rewrite it in terms of sine over cosine, and do some simplifying and end up with sine of px over sine of qx, and then take that limit, and that's going to give us the p over q in the same way. Okay, other questions out of 3.7?
Number 39.
Number 39. We've got a statement that says prove that the limit as x goes to infinity of e to the x over x to the n is equal to infinity for any positive integer n. All right, now the point of this problem is that they're really giving you 5,275 problems all in one and asking you to explain why all of the answers to all of those problems are equal to infinity. So, Aaron, what's your favorite power?
I don't know, how about 5?
5? Okay, let's analyze when n is equal to 5.
And it's kind of like I understand it, I just didn't know really what they were asking for in the proving of it.
Okay, so we'll talk about the example, and then
Okay.
we'll see how we can kind of make that into sort of a general prove kind of statement.
Okay.
Okay, so if we look at n is equal to 5, we have the limit as x goes to infinity of e to the x over x to the 5th. Alright, so I look at this, and as x gets really big, our numerator is getting big, and our denominator is also getting really big. So this fraction is of the form infinity over infinity, so we can use L'Hopital. So we'll take our derivative, and our numerator stays exactly the same, and our denominator is 5x to the 4th. And so now we've got e to the x over 5x to the 4th. Still don't really know what to do with it, but again, this is of the form infinity over infinity. As x gets really big, our numerator gets big, and our denominator gets big. So we can hit this guy with L'Hopital once again. So we've got the limit as x goes to infinity of e to the x over 20x to the 3rd. All right, our power is going down, but still we have an x in the denominator. In fact, if we do this 3 more times, then we're going to totally get rid of that x in the denominator. So let's go ahead and do that. We've got the limit as x goes to infinity of e to the x over 60x squared. We'll do it again. Limit as x approaches infinity of e to the x over 120x. Still, our numerator is going to infinity. Our denominator is getting larger, also going off to infinity. So we can apply L'Hopital again and get the limit as x goes to infinity of e to the x over 120. So at this point, by the way, at this point, we no longer have an indeterminate form. We now have the numerator getting extremely large and the denominator is staying right at 120. And so if you were to fall in love with L'Hopital, which we kind of did over here, I mean, we had this affair over here with L'Hopital, right? I mean, we kept applying L'Hopital time after time after time. If we continue to apply L'Hopital when L'Hopital should not be applied, your answer is going to blow up in your face. Okay, so you do not want to apply L'Hopital in places where applying L'Hopital is not valid. In other words, where you do not have an indeterminate form, you may not apply L'Hopital. Okay, so at this point we have a number on the bottom, and the numerator is getting larger and larger, and so our limit as x approaches infinity of this full fraction is equal to infinity. Okay, are there questions on calculating this limit before we talk about sort of generalizing?
So you can use any number if you were going to prove that on a test?
Well, so have we actually proven this for any positive integer? No. What we've done is we've looked at an example of one positive integer and shown that the limit is equal to infinity. Now, how do we prove that this works for any positive integer? What we need to do is to write out in words an explanation that says that this idea is going to work every time, no matter what your end value is. Some?
Derivative of e to the x is e to the x.
That's correct. Yep. So that's one nice thing is our numerator is always going to stay the same every time we take our derivatives. So, Aaron, what were your thoughts on this? Sort of like, what can you describe in general for this?
I kind of just thought, I just did kind of this, but I put different numbers in, and it made sense all, I guess with the positive, anything over, I guess, 1, anything like, I don't know, it's not really coming to words.
Okay. Well, let's start with the numerator, because the numerator, there's not a whole lot to be said about that. So let's say what we can about the numerator. So our numerator, no matter what our end value is here, that numerator is e to the x, and every single time we take a derivative, that numerator is still going to be e to the x. So, no matter how many times we take the derivative of e to the x, we get e to the x. So no matter how many times we apply L'Hopital, the numerator of this fraction is always going to be e to the x. No matter how many times we apply L'Hopital, the numerator is always e to the x. Now how about our denominator? Our denominator starts out as x to the n. Now when we had x to the 5th, we had to apply L'Hopital, let's see, 1 time, 2, 3, 4, 5 times to get down to a solid number with no x's left over. So if we have x to the n, how many times are we going to have to apply L'Hopital to get down to just a number? We're going to have to apply it n times. So after applying L'Hopital n times, our denominator is just a number, a constant. If you wanted to, you could be really specific about that constant. It doesn't really matter, it's just some number, so I don't really care that much about it. Okay. But if you wanted to be really specific, that denominator is 5 times 4 times 3 times 2 times 1. So in this case, this 120 right here is 5 factorial. And so over there, our denominator is going to end up being just an n factorial, if you want to be really specific about that. And so our limit, so after n iterations of L'Hopital, we have the limit as x goes to infinity of e to the x over some number. And since it's e to the x is getting bigger and bigger and bigger, and the denominator is just a number. So a huge number divided by a constant is still really big. So our limit is equal to. So what do we mean by prove something? Really, a proof is an explanation that describes why this formula makes sense. So if you can do that in words, great. If you do that in a formula of some sort, there are other techniques too, but words are fine for that.
Professor, if that number is even 1, it wouldn't make a difference, right?
This number on the bottom here?
Yes.
That's correct.
So it's basically e to the power of x that matters, where it's going to reverse infinity. Even if we think about it as a 1 underneath, it's just e to the x.
That's correct. That's correct. It's e to the x, and as x gets bigger, that e to the x is getting larger, and even if you have a 1 down here, or even if you have a million down here, e to the x is still getting bigger and bigger and bigger and bigger, and that million is just staying here.
Yeah.
And so, yeah. Jennifer?
So what happens when it's negative?
When it being...
Will it always approach a negative infinity?
Oh, as x goes to negative infinity here. So what will happen there in that case...
Well, I meant if n was negative, then it would always approach a negative infinity.
Well, if n is negative, if I have something like the limit as x goes to infinity of e to the x over x, let's just say to the negative 2. Well, now x to the negative 2 is really the same as e to the x over 1 over x squared. And so now my numerator is going off to infinity, but as x goes to infinity, 1 over x squared is going to 0, and so I have infinity over 0, which doesn't really work with L'Hopital, and we'd have to think about a different way of dealing with this.
Wouldn't you inverse that and multiply e to the x times x squared?
And so in that case, the way that we would want to treat this is we can think of this as the limit as x goes to infinity of e to the x times x
Right.
squared. And so
Right.
we could analyze this, and now when I look at this, e to the x is going off to infinity, and x squared is also going off to infinity, so a large number times a large number, this limit is equal to infinity without using L'Hopital at all.
Okay. But it would be different with x approaching negative infinity?
With x approaching negative infinity, this denominator is still going to ratchet down to just some number.
Okay.
And our numerator, actually,
Would that not work?
let me take that back. When x goes to negative infinity, our numerator is e to the negative large number, which is really 1 over e to a large number.
Okay.
So our numerator, limit as x goes to negative infinity of e to the x over x to the n. Well, depending on whether n is even or odd, will determine whether this bottom goes to positive or negative infinity.
Okay.
So that one's going to plus or minus infinity.
Okay.
But the numerator is actually going to 0.
Okay.
Because e, if you think about e to the negative 100, that's the same as 1 over e to the 100, which is a very tiny number. All right, so lots of questions about these limits, but these are good questions because we want to understand these properties. We want to understand what happens to e to the x, say, as compared to x to the 5th. And by calculating this limit and getting a value of infinity, what we're saying is that this e to the x function is growing at a much faster rate than x to the 5th. And by showing that this is true for for any or even every positive integer n, it says that e to the x grows much faster as x gets really big than x raised to any power, even x raised to the googol. Okay, so no matter what that power is, e to the x, the exponential function grows faster. All right, other questions or comments about this? Going once? Twice? All right. In that case, then what I'd like to do next